So the other day I dropped a camera into the deep sea and filmed this. This is a lantern shark, a small deep sea predator that glows. But that glow isn't just for looks, it's a weapon. For down here, light is the difference between eating and being eaten. And the more I looked into this, the more it became clear that in the deep ocean, light doesn't just exist, it dominates. In fact, scientists estimate that around 76% of all midwater marine life produces its own light. And these organisms aren't glowing by accident. Light is their language. It's how they find food, find mates, warn each other, talk to each other. But here's the thing about a language that everyone speaks. It can lie. Some of this light is a trap. And deep-sea predators have been using it to kill for hundreds of millions of years. But evolution is supposed to fix things like this. Given enough time, it should have produced something, some way to tell a real light from a fake one. Why hasn't it? Well, the answer turns out to be one of the strangest things I've learned about how life actually works. And who better to explain how light works in the deep ocean than the man that advised the team behind Finding Nemo?
Many of the other senses don't work very well down there. There's sound, they could be hearing things. Ideally, that's what they should be doing. There's not much of that. Smell doesn't transmit very well. Touch is of use in really short range, so you're kind of left with vision.
And this is why, in the deep ocean, the darkest place on the planet, light didn't just become useful, it became everything. So how does it work? Bioluminescence is a chemical reaction. Two molecules, luciferase and luciferin, combine with oxygen and produce light. No heat, no electricity, just chemistry happening inside a living body. But what blew my mind is just how many times this solution has evolved completely independently.
Yeah, it's evolved a lot. And every time there's a new paper that talks about it, I think in the beginning it was like 15, and then it was 40, and now it's 90. They keep finding evidence that, it's evolved many, many times. And it's really kind of the only solution once you get deep enough.
Up to 90 separate times, creatures that share almost no DNA arriving at exactly the same answer. You can't mate or hunt in complete darkness without light, so evolution kept inventing it. And here is what they're doing with it. Counter-illumination. The lantern shark's belly is lined with photophores, tiny light organs that produce a glow matching the faintest trace of sunlight filtering down from above. To a predator looking up from below, the shark vanishes. In shallower water, the bobtail squid does something stranger. It farms bioluminescent bacteria inside a light organ, feeding and cultivating them to eliminate its own shadow. Mating displays. The ostracod secretes dollops of light as it moves through the water. The speed, the pattern, the direction, it identifies the species. It's essentially a dance made of light in the dark. But the coolest one, by far, the burglar alarm. The Atolla jellyfish doesn't use light to hide or hunt. When attacked, it flashes a spinning wheel of blue, a distress call in the dark. Not to its attacker, to whatever might eat its attacker. It brings bigger predators down to eat the smaller ones. Which, is crazy. So light down here does it all. Finds food, finds mates, hides, hunts, warns. The only sense that works at depth. Which means it has to be trusted, and that is exactly the problem. So if light is a language that everything speaks, eventually something was going to use it to lie. And they did. The anglerfish. Now, I know you've seen this creature before, but stick with me, it gets weirder. The lure, that glowing thing dangling in front of its mouth, it's not a lamp, it's a modified dorsal spine packed with bioluminescent bacteria. It pulses, it drifts, in the darkness, it looks exactly like food. There are over 200 species of anglerfish, all with unique ways of using these lures. Some lures are large and round, some are branched and feathery, and some are so long they make the fish swim upside down. But all of them use their lures in the same way. Now unfortunately, I haven't managed to dive down to 1,000 meters yet to film this in the wild, but luckily the luring mechanism is exactly the same as in their shallower water relative, the frogfish. Prey approach, and prey die. But the siphonophore does something even more unsettling. It's a colonial organism, thousands of individual bodies, each one specialised for a different job. Some of those bodies form tendrils that dangle bioluminescent lures, and they look exactly like small crustaceans. Food. Prey swims in to feed, the colony closes around them, and they don't swim back out. And then there's the fish that broke all of the rules. So most deep sea animals can only see blue light. Their visual systems are locked to a narrow range of wavelengths because that's the spectrum the ocean lets through. Red light doesn't penetrate very deep. So by that logic, red bioluminescence should be invisible to everything down here. But one fish decided to exploit that. The dragonfish developed light organs with red bioluminescence, a private wavelength invisible to 99% of animals in the deep. And then, uniquely amongst deep-sea fish, it evolved the visual pigment to see it. The dragonfish cracked the code. It made its own private light and hunts in a spectrum that its prey literally can't see. So now we've seen how light is used to attract, to hide, to deceive, to hunt, to escape. But here's what matters. Watch an animal in the deep being drawn towards light. It's not being stupid, it's doing exactly what it has to do. Following light is how it finds food in total darkness. Following light is how it finds a mate. The animal approaching the lure isn't making a mistake. It's just following the rules that have kept it alive since before the dinosaurs roamed the earth. But these same rules are exactly what has programmed them to die. So here's my question. Predators have been using bioluminescent lures to catch their prey for hundreds of millions of years. And in every single generation, some prey animals follow light, and they die. But across nearly every other animal on Earth, evolution has solved this problem. Snakes are feared, animals avoid fire, and predators are recognised by their shape. Evolution fine-tunes what to avoid. But not in the deep sea, not for hundreds of millions of years. Evolution has had countless generations to fix this problem, but it hasn't. Why? Let's start with the obvious one. They literally can't tell the difference.
Most of the animals down there are colorblind. The other thing is that their visual systems are not very sharp. There's a trade-off in low light between having sharp vision and having sensitive vision. So they're not seeing a color, they're not really seeing a shape. They're also a little bit limited in how fast they can see, like their shutter speed. And that's kind of doesn't leave much, right? You know, you don't have enough information to know if it's a safe thing or not, but you gotta eat. You got a mate.
You can think of it a little bit like the pixels on your phone's camera. You can have millions of tiny pixels and get a sharp image, or you can have a few large pixels that gather enough light to actually see in the dark. Deep sea eyes chose the large pixels. They can see, but they can't see much detail. So a bioluminescent lure and a bioluminescent mate look identical. But even if you could somehow tell the difference, here's the second problem.
Basically, what are the chances of you getting your lunch versus someone else making you their dinner?
If 99 flashes are food, and only one is the flash of an anglerfish's lure, following light is still, statistically, the correct strategy. The odds are in your favour. Evolution doesn't select for perfect choices, it selects for good enough, even if sometimes that means dying. But there's a few other answers worth mentioning. Maybe the lures evolved recently enough that prey hasn't had enough time to adapt yet. Maybe the deep sea's slow metabolisms and long generation times mean adaptation just runs slower down here than anywhere else on the planet. Maybe the animals that followed every flash out-reproduced the ones that were more cautious. Each one of these is probably a little bit true, but none of them are the complete answer. The complete answer is much stranger. So we tend to think of evolution as a process of improvement. Each generation a little better, a little more refined. But that's not how natural selection actually works. It has no destination. It doesn't improve things. It just keeps what worked well enough yesterday. And sometimes, more often than you'd think, a single trait can do two jobs at once. One good, one bad. And evolution can't touch one without affecting the other. Here's an example from your own body. Testosterone in men builds muscle, drives competition, and supports reproduction. All of it useful. It also suppresses the immune system, increases cardiovascular risk, and shortens lifespan. Evolution can't remove the costs without also removing the benefits. You are built to reproduce. You are not built to live forever. And then there's this example. 3,000 meters below the surface, an octopus mother stops eating after laying her eggs. She slowly cannibalizes her own body. The same hormonal cascade that drives the protective instinct drives the starvation. The behaviour that gives her offspring their best chance of survival is the behaviour that kills her. But the Pacific salmon does something even more striking. After it spawns, its own body breaks down, deliberately. Cortisol floods the system, organs fail, the carcass decomposes in the stream, feeding the ecosystem its offspring will need to survive. Evolution isn't optimizing for your survival, it's only keeping what reproduces. Now, let's bring it back to the deep sea. The instinct to follow light isn't separate from the instinct to find food. It isn't separate from the instinct to find a mate.
Sort of like a party in the dark, and imagine that party is prowled by panthers. And the panthers have like a little, light on their collar. And, you have to decide, am I going up to, the person who's going to be, my partner for life? Or, am I going to get eaten? They're kind of stuck. I just think they're stuck.
So the deep sea isn't shaped by what evolution can fix, it's shaped by what it can't fix. But here's the thing, evolution didn't stop there. Prey did adapt. They started using light to hide from things that were using light to hunt them. The lantern shark's counter-illumination, the bobtail squid's shadow-cancelling bacteria. The same tool turned around. But then, of course, predators adapted to that. Ultra black skin. Some deep-sea fish have evolved skin that absorbs 99.9% of light. No reflection. Effectively invisible, even when a bioluminescent beam hits them directly, including the light from their own weaponry.
You can think of it in terms of an arms race, We don't know a lot about sort of the evolutionary history of that, like what came first, did like ultra black skin predate, directed bioluminescence. We don't know it, we just know that they do work in opposition to each other.
We don't even know which came first, attack or defense. That's where we are. And then there's the dragonfish, which, remember, cracked the code, evolved a private wavelength. For now, it works, but only because nothing else has evolved to see red. Yet. The deep sea definitely isn't an ecosystem in balance. It's an arms race. Nobody's stopping, but nobody's winning.
It's a different world down there, and so, like on land, a full-grown buffalo is not going to eat a baby lion. In the ocean, it's more likely that anybody bigger than anyone else will just go ahead and eat them. And so you really don't know. I mean, you're just taking a chance when you come up on something.
So every organism down there is both prey and predator. Hunting by light, hiding from light, and using light to find a mate, whilst also trying to avoid predators that eat them using light. The game seemingly never ends. It never declares a winner. It just keeps escalating. So, if evolution can't fix the most fundamental predation problem in the deep sea, a problem it's had hundreds of millions of years to fix, what other systems down there are permanently locked in by trade-offs we haven't found yet? The deep sea covers more than half the surface of this planet. We've explored almost none of it. We are only at the very beginning of understanding what evolution can and can't fix down there. I wonder what else might be stuck.